Let's begin with weather and climate. The oceans and the atmosphere are the two large reservoirs of water in the Earth's hydrologic cycle, and so they're very linked to climate and weather. Really, they're responsible for each other as well. The oceans regulate the temperature in the lower part of the atmosphere, and the atmosphere is responsible for circulating the ocean water. Let's define weather. It's the condition of the atmosphere at a particular time and place, giving the temperature, pressure, humidity, precipitation, and wind velocity. Weather is controlled by the properties and movement of water in the water cycle. And because the amount of heat varies with the location and the amount, the atmosphere is in constant motion, thus weather is very dynamic and complex. And it's another reason why meteorologists have such a difficulty predicting it. Climate refers to the average weather characteristics of a given region, and anywhere from a local to a regional to a national scale, even hemispheric scales. Climate changes over longer periods of geologic time and is more stable over short periods of time, like years and centuries. The unfortunate thing about climate for us is that we really only have solid climate data for like the last 100 years or so. The Earth's weather and climate represent complex interactions between the oceans, the land, the sun, and the atmosphere. And as I said before, meteorologists have a difficulty predicting the weather as a result. Understanding climate is even more difficult because of our only having recent data to describe the climate cycles, which operate on such a larger scale and longer scale. Climate uses temperature and precipitation to really kind of map out the climate zones. If you take a look at this map, we have the general tropical climates, mid-latitude climates, polar climates, and you can see the differences and where they're at. And this one is a good one because it also gives the ocean currents and the cold current versus warm currents and how those might affect some of the climate situations on some of the land masses. But in summary, you can kind of just take a look at this and see where all the different climates are in general. Let's take a look at those specific climate zones. The tropical climates are in the reds and yellows and oranges, and those are generally represented right along north or south of the equator. We have the mid-latitude climates, anywhere from 30 to 60 degrees north and south latitude, given in green tones, and then the polar climates, they are generated in purples and white for polar ice cap, kind of give you an indication of where some of those things are around the world. We can certainly pinpoint macroclimates, which is what we just looked at in the last slide, but microclimates are a different entity altogether. Microclimates are really just your specific local climate. Even though we are in the humid continental climate, we would all have different microclimates depending on our particular region. For example, the lake affects the weather near Chicago, whereas out further west of Chicago, the climate is less affected by the lake and more so by either the presence or lack thereof, farmland and things like that. Microclimates then are influenced by things like latitude, proximities to large bodies of water, elevation, and density of vegetation. Microclimates tend to change the most when there's even a small shift in the overall global climate conditions, which is why we see so many different peoples around the world being affected differently by the globe warming. Human history is very short compared to the global climate change timescales. And so as a result, climate change is not very well understood. Scientists have tried to use general circulation models with computers, incorporating millions of pieces of data to help sort out the complex sets of variables that influence climate. Models predict temperature, precipitation, wind patterns, sea level changes. One thing that the models have been able to generate is a few very concrete things that actually do have a significant effect on the climate and the change of the climate. And those things are the position of the continents through the movement of tectonic plates, the changes in Earth's orbit around the sun and those oscillations and how they produce more or less solar radiation, volcanic eruptions, and human activity. And so we're going to discuss each of those as factors in climate change. Let's discuss first off the natural climate change factors of plate tectonics, astronomy, and volcanism. For millions and billions of years, the continents have been moving around on the surface of the Earth due to plate tectonics. You see the picture over here on the right of Pangaea, when all the lands were put together at one point, sometime around 250 million years ago. At about 200 million years ago, they begin to drift apart and have done so until they have reached their current position for the present day, as you can see on the bottom. The changing position of the continents changes wind flow patterns, global ocean circulations, and affects the temperature and precipitation patterns all over the world. If a continent drifts toward the equator, the climate will become warmer. If it drifts toward the poles, it'll become colder, and different types of animals will live there and be available to live there. And in addition, the presence of lots of continents on the equator versus lots of continents near the poles, and how they can maintain maintain land ice versus sea ice, and how that affects the reflectivity of the sun. There's lots of complex things involved in where the continents are, and so they're a very important factor in climate change. And as a result, we have seen the climate change very cyclically and very frequently for the past, well, ever since we have rock records of it. Climate change is also because of astronomical factors. The Earth's orbit around the sun is not perfect. It goes through certain oscillations. These oscillations were studied by a scientist named Milankovitch, and so they're named after him, the Milankovitch cycles. And they involve three particular oscillations of the Earth in its orbit around the sun: the eccentricity, the obliquity or tilt, and the precession or wobble of the Earth. Eccentricity is the change in the ellipticity of the Earth's orbit. Earth's orbit becomes more and less elliptical around the sun based on a cyclic pattern of about every 400,000 and 100,000 years. The Earth's tilt has also been seen to have changed in the past. The tilt has been shallow as 22.2 degrees and as deep as 24.5 degrees. The greater the tilt, the more extreme the seasons, and the more effect that then has on the reception of solar radiation on the Earth's surface, be it on the equator or on the poles. And again, depending on continental position, that's going to have a large effect on climate and climate change. Lastly, the Earth wobbles on its axis to the tune of about every 26,000 years. Right now our pole star is Polaris. The Earth's North Pole actually wobbles, and it traces a circle in the background of the stars in space. And so 13,000 years from now our North Star will be Vega, and then in another 13,000 years Polaris will be our North Star again. This is the concept of precession, or the wobble of the Earth. And this also affects the amount of sunlight and where the sunlight is received on the Earth's surface. The combined effects of the astronomical variations results in climate changes similar to those observed for glacial and interglacial periods that we've seen in the evidence of the rocks and the fossils and the ice cores and the data we receive from those about the atmosphere, all the way back to almost 500,000 years ago. And we can see some clear patterns in the fluctuations of the amount of solar radiation received by the Earth, and also the amount of carbon dioxide in the atmosphere and the amount of temperature in the atmosphere. This is a graph showing the fluctuations in the Earth's orbital shape and how it becomes more and less elliptical. And you can see those more and less ellipticities have an effect on the overall shift in temperature of the planet. And you can also note that the temperature actually rises. If you start from the diagram on the right and work your way to the left, temperature rises first, and as the temperature starts to rise, then the CO2 starts to rise. So interestingly enough, as the Earth's orbital shape becomes more elliptical, the temperature rises, and as the temperature rises, the CO2 begins to rise. The temperature peaks out first, and then begins to fall. Then the CO2 peaks out, and then begins to fall. It appears that the CO2 follows the temperature rather than leads it. Now there is one anomaly on this, and that is the present day. You can see the CO2 has followed the temperature up, but in the last 100 years or so, there's been a big blip in the CO2 amounts. It has spiked to record levels there, more so than we've seen in the temperature record of the past. But you can also look back and see that the temperature has actually been warmer than it has been today. And you can also see that the globe is warming. The globe has been warming for the last 10,000 years. There is global warming. Global warming is a thing, and it's happening, and the globe is warming. So that also can be seen in this graph. It can be seen that the globe warms and the globe cools cyclically. So you can't say that there isn't any global warming. There is. It's happening today, and it happened at about 125,000 years ago, and again at about 240,000 years ago. Volcanic eruptions also behave in such ways that will help to shift the climate. The size, type, and duration of volcanic eruptions have a significant effect on the atmosphere. CO2 has a warming effect. SO2 or sulfur gases have cooling effects, and dust particles have cooling effects, and chlorine gases can contribute to ozone depletion in the upper atmosphere. The eruption of Mount Pinatubo in 1991 and El Chichon in 1981 released large quantities of dust and sulfur gases in the air, and it really reduced the amount of solar radiation reaching the surface. Thus, there was a short-term cooling of the atmosphere. And in 1815, there was such an intense injection of dust and sulfur dioxide in the atmosphere that the eruption of Mount Tambora was responsible for calling 1816 the year without a summer. And scientists have seen evidence that major eruptions throughout the Middle and Late Cretaceous produced large quantities of basalt flows, particularly in the Deccan flood basalt flats and plateau of India. But so much CO2 is thought to be released there that it contributed to some of the warmest temperatures in Earth's history, with sea levels much higher than they are today. Let's take a look at what humans have as far as an effect on the climate. Pollution from transportation and industry releases carbon dioxide into the atmosphere. Carbon dioxide, being a greenhouse gas, will absorb heat. Thus, release of carbon dioxide helps to warm up temperatures. This is known as the greenhouse effect. Greenhouse gases absorb heat energy and hold it with them in the atmosphere. Actually, greenhouse gases are necessary for life to exist on this planet. If we didn't have greenhouse gases holding heat and distributing it around the planet, we wouldn't be able to have life as we know it. Greenhouse gases then keep the atmospheric temperature relatively stable. The problem with greenhouse gases and human activity is that there's been an increase in the input of carbon dioxide into the atmosphere by burning of fossil fuels. Carbon dioxide actually makes up a very small percentage of the atmosphere, less than 1%. Actually, a more important greenhouse gas would be water vapor. Water vapor exists anywhere from up to 4% in the atmosphere. So water vapor, being greenhouse gas, absorbs a lot of heat and solar energy and energy from the sun. Thus, water vapor is really one of the most important greenhouse gases that we have out there. The CO2 that's released into the atmosphere is mostly related to energy use, and that's kind of shown in the figure below there. We do know that the CO2 concentration in the atmosphere has been steadily increasing at an unusually high rate since the mid-1800s, and this correlates well with the burning of fossil fuels for electricity and industry. We also note that the record for the past 100 years of temperatures shows an overall average increase in global temperatures by about 0.5 degrees to 1.0 degrees C or so. The difference in global temperature between the coldest period of the last glaciation and the present was about 7 degrees C. So just to give you an idea, it's a really small blip in the increase in temperature, but it is significant in the fact that it's happened in the last 100 years or so. Scientists are able to compare the current fluctuations in temperature and greenhouse gas concentrations to that of the past. We don't have temperature data, direct temperature data for more than like 100 years ago. And so what we have to do is use a more clever means of obtaining temperature and carbon dioxide data. And so what scientists do is they drill a hollow drill tube into the ground, specifically into the ice, in the glacial ice. And they pull out a core sample like you see pictured here. These core samples have layer upon layer of snowfall for every year, and the snowfall layers freeze bubbles of atmosphere within them. And so we actually have little samples of the atmosphere that go way back to almost 500,000 years ago. This gives us good carbon dioxide and methane and temperature record data. And it's very interesting that we can use this information to fill in the gaps of information from the lack of direct measurements prior to about 100 years ago. The graph pictured here is what the results from the ice core data show. The concentration of greenhouse gases directly correlate with the average global temperatures throughout time. We see that as the temperature rises, the CO2 rises, and the CH4 rises, that's methane. And then so too does the oxygen isotope ratios. The oxygen isotope ratios are temperature markers that help guide us. The sun cycles are also positioned on this graph at the bottom. This graph goes from 400,000 years or so on the right to the present on the left. And you'll note that in the present time, for the last 10,000 years or so, the temperature has been rising, so has CO2 and so has methane, long before any burning of fossil fuels was present. But we do note that over the last 100 years or so, we see a rise in CO2, and that's the topmost graph. We see a rise in CO2 at the very close present. It is of note that during the last 150,000 years and beyond, that we've had glaciations and interglacial periods due to this temperature rise and fall. And the temperature rise and fall has been a natural phenomenon for the last 400 plus thousand years, and scientists argue since the Earth began, really. There's been temperature fluctuations due to different natural events, not only the Earth's oscillations, volcanism, and the continental positions, but I'd also add a fourth there, and that's solar cycles. The way the sun behaves is a new place of study that scientists are researching, that indicating that the sun gives off more or less solar radiation at different times for different reasons in a cyclic fashion. But it is of note that the Earth has gone through glaciation and interglacial periods since it began, noting that we had a glaciation period from about 70,000 years ago to about 10,000 years ago, and then we've had a steady warm-up to our current interglacial period that we have today. So we are already currently in an interglacial. We would expect temperatures to rise, and they are. We talk here about how the dust in the atmosphere was higher during interglacial periods, thus heat was likely to be reflected back to the Earth's atmosphere back into space. And it's really not known if low greenhouse gas concentrations and high dust content in the atmosphere cause the ice ages, or if these conditions were caused by the ice ages. But there's still some question marks out there. Thus, it is widely known and accepted that the globe is warming and that the CO2 concentration is rising. The debate lies in whether or not human activity is the cause, and the debate also lies in the extent of the effects of global warming on the different microclimates. Let's talk about the effects of climate change. The effects of climate change, specifically the globe warming, because that's what's relevant for us today, is that sea level will rise. Melting of some of the land-based ice will cause the sea levels to rise. Reduction of sea ice will occur, and when the sea ice is reduced, that produces an effect where more sunlight is absorbed by the oceans. When you have a lot of sea ice, a lot of that sunlight's reflected back into space, but when you get rid of it, more of the sunlight gets absorbed by the Earth's surface, so it causes a greater warming effect. Also, changes in the hydrologic cycle would occur. Perhaps more global precipitation changes as well. Maybe some increased storminess, change of temperature of some of the climates, changes in vegetation patterns and precipitation patterns globally and regionally. And then thawing of frozen ground would likely release some CO2 and methane in the atmosphere, causing even more warming. So there will be some interesting effects that occur there. It is of note that one of the great regulators of temperature and carbon dioxide on this planet is life. Life has been regulating the carbon dioxide in our atmosphere for really since it's existed billions of years ago, and it continues to do so today. So that's one unique thing about our planet, is that we have the great regulator of life. Most recently, humans have been adding carbon dioxide to the atmosphere, and it has had a warming effect. To what significance of that is where the debate lies, and also how great will these effects be? That's also part of the debate that we just talked about earlier. So what can we do? Well, many countries are working together to reduce the potential effects of global warming. Treaties and laws have been passed to reduce pollution. Even community projects to reform areas have been developed at a local level. These are very good efforts and very useful. Pollution is caused mostly by the burning of fossil fuels, so running automobiles less and using electricity will help. We can have a significant effect on the pollution rates if we just simply turn off the lights when we're not using them, turn down the heat in the winter, reduce the air conditioner use in the summer. These things all help. We know that the globe will warm and cool naturally over time, but it's really not necessary for us to think that we don't make a difference. We can make a difference in the things that we do, and it's always good to live synergistically with your environment, no matter how severe or not severe the effects of global warming will be on our planet and our civilization. Public transportation is another thing we can use. Puts less CO2 in the atmosphere. All vehicles burn fuel more efficiently if they are properly tuned and the tires are properly inflated, and of course hybrid cars, gas engines help. So that's a look at climate and climate change. A couple of take-home messages here: that the Earth has climate zones, that they are difficult to nail down because we only have data that goes back about 100 years. We do have advanced data from ice cores that give us climate markers all the way back to 500,000 years ago. We do see natural cycles and natural climate change, plate tectonics, continental position, astronomy, including the Earth's position and the sun's cycles, and volcanism. These all have an effect on the climate and have had since the Earth began. We have seen evidence of this for the last 500,000 years or so in the rocks and glacial evidence and the polar ice caps and such. And humans have an effect on climate change. Humans do have an effect in that we release a lot of carbon dioxide in the atmosphere, and that does have a warming effect. To what degree that warming effect is and how much that'll create effects is under debate. But nonetheless, it's always important to live synergistically with your environment and sustainably. And these are definitely things that we need to work on as humans to make our Earth a sustainable place for future generations. So that's all for climate today. Thanks for listening, and I look forward to seeing you or talking to you, I guess, when we study the atmosphere.